Hello there. This is Professor Lapuz, and we are going to take a look at the process for a singular value decomposition. So, in the theory part, we'll discuss what a singular value decomposition is, and that is essentially a way to decompose a matrix. Now, the idea is, let's first define what a singular value is. So here it says that if A is an m by n matrix, and it is important to note that this does not have to be a square matrix. If you have an m by n matrix, then the singular values of A are going to be all the positive eigenvalues of not A, because A is not a square matrix, but A transpose times A. So A transpose times A, regardless of the size of A, is going to end up being a square matrix. Not only is it a square matrix, but it is also going to be a symmetric matrix. So let's just verify that you're going to get a square matrix in that if you have A transpose times A. So A is an m by n matrix. So A transpose is going to be an n by m matrix. So A transpose times A is going to be an n by m matrix times an m by n matrix. So A transpose times A is going to be an n by n matrix. So it's going to be a square matrix. And again, it's going to be symmetric. So we're going to be guaranteed some real values, eigenvalues. So real, not just real, but positive eigenvalues. Okay. All right. The idea behind a singular value decomposition, which from now on we'll call SVD, is going to be a way to write A as if you were trying to diagonalize it. Now, the idea of diagonalizing this doesn't quite make sense because, again, it's not necessarily a square matrix. But the idea here is to diagonalize it so that one of the matrices looks like a diagonal, even though it's not necessarily a square matrix. So let's find out what that means. So this decomposition was going to be the focus of this talk right here. All right, proposition tells us that if you have an m by n matrix, then A transpose times A and A times A transpose will have the same eigenvalues. So that is very interesting that they have the same eigenvalues. It's almost like assigning an eigenvalue for A. And so here's how the decomposition is going to work. A singular value decomposition is that we'll start off with an A, m by n matrix A, and then we're going to try to write that product or write A as a product of three matrices. So again, it's like diagonalization, but because the sizes are going to be different, we're going to have to work this out carefully. So it's going to be U times the matrix sigma. Now I know we're used to seeing this symbol as if it was a sum, but we'll use this as a name of a matrix, sigma. U is going to be an m by m matrix, and that will end up being an orthogonal matrix whose columns are going to be eigenvectors of A times A transpose. V is going to be an n by n orthogonal matrix whose columns are going to be the eigenvectors of A transpose times A. So remember, we have an orthogonal matrix. When we diagonalize a regular square matrix, it's going to be, I think it was P times D times P transpose. So instead of P and P transpose, because the diagonal is not going to be a perfectly square matrix, these two matrices, P and P transpose, or in this case is going to be U, and a different vector or different matrix V transpose, will have to be different sizes. And so you can see that U is going to be an M by M, V is going to be an N by N. And then sigma, this is your non-square matrix, is going to be kind of a diagonal. And I say kind of because we have singular values. The diagonal is going to be made up of the singular values of A. So not quite the eigenvalues, but rather the square root of the eigenvalues, because that's what the singular values are. And it's going to be the same size as A. And then what is this? How is this expressed? Sometimes it's expressed this way. It's going to be the sigma matrix is going to be expressed this way, where you have a bunch of zeros, except you have sigma in the upper left-hand corner. Now, this is technically not a 2 by 2 matrix, but rather a more complicated matrix. And so the sigma, this is actually not just one element, but a diagonal matrix. And then the number of zeros that we have for the rest of the columns and rows will depend on the size of the matrix. So that might sound a little confusing, but let's see how this goes. Let's take a look at, again, A is an M by N matrix. So if we take a look at A transpose A, I think, is that the one we did? We did A transpose A, and we ended up getting an N by N matrix. So we saw that earlier. Now, A transpose A will give you an N by N matrix. So this is going to be a square, and symmetric matrix. Symmetric. And so we're going to get eigenvalues for that. Now, if we take a look at A times A transpose, A, remember, was an M by N matrix, and then A transpose was an N by M matrix. So this will end up being an M by M square matrix. So this is also going to be a square, symmetric matrix, which means it'll have it'll also have eigenvalues and eigenvectors. Now, whichever size is bigger will kind of depend on how we're going to approach the problem. If M is bigger or if N is bigger, then that's what we're going to have to deal with. Now, your sigma will be an M by N matrix. All right. So let's see how that's going to look like. The product is going to be U, which is going to be the same size as U, the same size as A transpose, so that's M by M. Sigma is going to be the same size as A, N M by N. And then A transpose A is V. V transpose is, since it's a square matrix and it's an orthogonal matrix, the transpose is the inverse. So V transpose is going to be the same size as A transpose A, which is an N by N. And just to make sure that we can actually do the matrix multiplication here, when we multiply these things, we should end up with the same result or the same size as A. So if we multiply U times sigma, the M's will cancel. If you multiply sigma times V transpose, the N's will cancel. And then so U will end up, or A will end up being an M by N matrix, which is what the size of A was. Okay, so the sizes work here. And let's just take for an example, if A was a, let's say a 3 by 4 matrix, and then you got your eigenvalues. Let's say you have 3 non-zero eigenvalues. So sigma 1, sigma 2, sigma 3. And so your singular values, so these are your E values or eigenvalues. Your singular values will be sigma 1 will be the square root of lambda 1, sigma 2 will be the square root of lambda 2, and sigma 3 will be the square root of lambda 3. All right, so you have 3 singular values, but then your sigma matrix should be a 3 by 4. So 1, 2, 3, 1, 2, 3, 4. So this should be the size of your matrix. So you're going to have your sigma 1, sigma 2, and sigma 3 go in the diagonal, and then everything else would be 0. So if we fill in the rest of the zeros, we're going to actually have the last row. Oops, I think I drew one too many zeros there. The last column would be a column full of zeros. And then we have these things. So this is a 3 by 4 matrix that would satisfy this form of sigma. Okay? So that's the idea behind creating your matrix. Another important part that would be useful when we're creating these things is that the rank of your matrix A is going to be equal to the number of singular values. So the number of non-zero eigenvalues is going to be the same as the rank of your A. So if you know the rank of A, then you know to anticipate the number of singular values that you have. All right, that's the deal. That's the background, and let's do an example. So here's our example. This is our A. Let's find out the couple of things that we need to find out. So what do we need to find out? We need to find out A and A transpose. So A transpose, and then we need to multiply that both ways. So let's first find A transpose. This is going to be 1, 2, 0, 2, 0, 2. All right. So now let's figure out the 2 matrices that we need. Let's see. Let's do A transpose A first. A transpose A, and that would be A transpose A would be, let me write down the sizes of these matrices. This is a 2 by 3, this is a 3 by 2. So A transpose A would be a 2 by 2 matrix. So A transpose is first. It's the first column, first row of A transpose times the first column of A. So that's 1 plus 2 times 2 is 4, so that's 5. And then the next one, the first column, and the first row and second column, so that's going to be a 2, 0, 0, so that's a 2. And then 2, 0, 0 times that is going to be a 2, and then the last element would be 2, 0, 2 times 2, 0, 2, so 2 times 2 is 4, 4 plus 4 is 8. So this is our A transpose A, and as expected, it's a symmetric matrix, it's a square matrix. All right, A times A transpose will end up being a 3 by 3 matrix. So this first, so 1 plus 4 is 5, and then we have 2, and then we have 0 is 4, and then second row, first column is going to be a 2, not a surprise because this is supposed to be symmetric. Then 2 times 2 is 4, and 0, and then 2, 0, 0, so this is going to be a 0. and then the last one is going to be a 4, and then it's going to be a 0, and then it's going to be a 4. Okay. All right. So we can find the eigenvalues and eigenvectors of each of these. Let us find the eigenvalues and eigenvectors for the first one. So A transpose A. So E values for A transpose A, and that is going to be, let's do it all by hand from scratch. This is going to be 5 minus lambda, 2, 8 minus lambda. And so if we find the determinant of that, the characteristic polynomial would be 5 minus lambda, 8 minus lambda, minus 2 times 2 is 4. So this is going to be, let's see, 5 times 8 is 40, minus 5 plus 8 is 13, and then plus lambda squared minus 4. So this is lambda squared minus 13 plus 36. And if we set that equal to 0, this is going to be lambda and then two numbers that multiply to 36 add to 13. They both have a negative sign. How about 9 and 4? And so those are our two eigenvalues. So lambda equals 9, lambda equals 4. All right. I was going to be interested in finding the eigenvalues for A times A transpose, but we should also get 9 and 4. In fact, we're going to get a third one that's going to be 0. Let's hold that off for a second and figure out our eigenvectors for each of these things. So when lambda is equal to 9, our matrix is going to be 5 minus 9. I think that's negative 4. 2, 2, and then 8 minus 9 is negative 1. So we're expecting this to have non-trivial homogeneous results. So I think if we make this into a negative 2 and a 1, or let's go all the way, make it into a 1/2. Let's try that again. So if you row reduce, this is going to be 1, this is going to be negative 1/2. This should be 0, 0 because they're linearly dependent. And then so we have 1, and then this is going to be positive 1/2. And so let's just scale that up to 1, 2, and then I'll find the the appropriate size for that. Well, I'll find it now. So the magnitude of this vector is going to be the square root of this is 4 plus 1 is 5, so square root of 5. So remember, these are the eigen. If we go back to this, we went A transpose A, so we're looking at V here. So V1, I'll say V1 is going to be the first column of our matrix V is going to be 1 over root 5 and then 1, 2. Okay, now let's find the 4, the eigenvector associated with 4. And so let's subtract 4 there. So 5 minus 4 is 1, 2, 2. 8 minus 4 is 4. And you can see that they would make that go away. 1, 2, 0, 0. Oops, this is a 4. Okay, so you will have 1 for your free variable, and this will go with -2 for that. And just to make sure that these are orthogonal, if you take the dot product of these two vectors, you're going to get 0. And to make sure that they're orthonormal, you divide by its magnitude. The magnitude, again, is going to be 5, or square root of 5, so this is 1 over root 5, -2 and 1. So I think we can confidently say that our vector v, or our matrix v, is going to be made up of these two vectors. So let's see, 1 over root 5, 2 over root 5, and here it's -2 over root 5, and 1 over root 5. All right, so we got v. Now let's go to, oh, by the way, since we do have, well, let's take a look at let's work on this matrix now and explore its eigenvalues and eigenvectors. And I think I've already mentioned that we should expect the eigenvalues and eigenvectors for this matrix to be the eigenvalues and eigenvectors of this matrix to be the same as the other one, which means there's an extra one. So I think the extra one is going to have to be 0. Let me just change the color of this. So let's find the eigenvalues and eigenvectors for that. So E values. So we'll take a look at 5 minus lambda, 2, 4, 2, 4 minus lambda, 0, 4, 0, 4 minus lambda. Let's see. So a characteristic polynomial is going to be a little bit messy. Let's try expanding on the last row. So this is a plus minus plus. So this is going to be a 4 times, let's see, we cross that out, we get 2, 4, 4 minus lambda, 0, minus 0 times something plus 4 minus lambda times 5 minus lambda, 2, and this is a positive 2, and then a 4 minus lambda. All right, so this will give us a 4 times 4 minus lambda times 4, I believe, and we got a 0 here, and then we have a 4 minus lambda, and then we have a 5 minus lambda, 4 minus lambda, minus 2 times 2 is 4. All right, let's continue working on that. Let's see if we can simplify it a little bit more. This is going to be a 16, 4 minus lambda, plus, let's go 4 minus lambda. Let's see, let's FOIL this out. This is going to be 20 minus, this is 5 and 4 minus 9 lambda, minus lambda squared, minus 4. So this is going to be, this is the plus lambda squared, so lambda squared minus 9 lambda minus 16, and then we're going to multiply that by 4 minus lambda, so this is going to be 16, 4 minus lambda. I'm not going to multiply it out because I'm anticipating lambda minus 4, or 4 minus lambda, to be a factor. And yeah, so why don't we just factor that out? 4 minus lambda, lambda squared minus 9 lambda minus 16. So if we factor that out, we got 4 minus lambda, and then we have a, what do we have left? We have 16 here, and then times or plus lambda squared minus 9 lambda minus 16. So we got the 16 minus 16 to cancel, and then now we have lambda squared minus 9. So we got 4 minus lambda, lambda squared minus 9 lambda, so the lambda would just go away. So as anticipated, we have lambda is equal to 4, lambda is equal to 0, and lambda is equal to 9. So we got the same 4 and 9 there, and then we just have the 0. Okay. All right, so now that that's settled, we know that the eigenvalues for this is 9, 4, and 0. The eigenvalues for the first one was 4 and 9. So we can actually create our sigma and our singular values. So our sigma with the singular values, I'll put it right here in the middle, will be 9, the square root of 9, which is 3. And it has to be the same size as a, so it'll be 0, 0, 0, and then the square root of 4 is 2, and then 0, and then that's it. All right, so just to confirm where these things came from, this is the square root of 9, the square root of lambda 1, and the square root of 9, and then this is the square root of lambda 2, which is going to be the square root of 4, which is equal to 2. So those are our two singular values. All right. Now we have V. Let's circle this. And then we have sigma. Let's try that again. We have sigma, we have V, and we have sigma. And now we need to find U. So U will have to be a 3 by 3 matrix, and it would be the eigenvalues of this matrix that we found, A times A transpose. That's one way to find it. Another way to find it is to use some connection with this equation. Let's see, we have an equation. A is equal to U times sigma times V transpose. And if we multiply by V on both sides, since V, the inverse of V is V transpose, then AV is equal to U sigma. And so sigma, by the way, each of these columns of U, we'll call it U1, U2. I'm going to write it as a vector because these are like, that would represent the columns. And then U3. We know that this is going to be a 3 by 3 matrix, so it's going to have 3 columns that we're looking for. And if we multiply this by sigma, remember sigma, we already have sigma, and that was that kind of diagonalized vector that has a 3, 0, 0, 2, and 0, 0. And so if we do the matrix multiplication here, so this would be a 3 by 3, or this would be a 3 vector here. The U is going to be a 3 vector, and it's going to be a 3 column. Then each of these columns would just be kind of multiplied by, what are we going to get? We're going to get a 3 by 2 matrix here, and each of these would be multiplied by the sigma. And what we're doing here, let's look at the sizes again. This is a 3 by 2. This is a 2 by 2. And so we expect this to be a 3 by 2 matrix. And when you do this multiplication, this is a 3 by 3, and this is a 3 by 2. So again, it's going to be a 3 by 2 matrix, right? So if we take a look at this, the number of columns here, this is going to have 2 columns, and I think the matrix multiplication of this, let's see, is going to be multiplying A times the columns of V, so that's V1 and V2, which we already have over here. And so when we're trying to identify U1, U2, and U3, at least the first 2 columns would be obtained by dividing out by this sigma. So what does that mean? That means we can't take the inverse of this thing, but each of these columns would be represented by the square root of sigma. So I guess what I'm trying to say is that at least the first 2 columns of this could be represented by U1 is going to be the first columns of this, A times V1, but then this will have a sigma in it. And so since sigma is just going to be the first column that's going to be involved there, we can write U1 to be equal to the reciprocal of sigma 1 times A V1. Since we have A and V1 already set, this might be an easier way to find U. This is not an equal sign here. Let's make that correction. I meant to put an arrow. And so that's a way to find U. And then similarly, you can find U2, the second column, to be 1 over sigma 2 AV2. Now, since we don't have a third column for V, we have to find U3 another way. And the way to do that essentially is to kind of extend these 2 vectors. They're supposed to span R3, since this is going to be a 3 by 3 matrix. So we can take these 2 vectors that we've already found and find another third vector that's orthogonal to these 2, and we can do that by just making up another vector for U3. Well, we can't make it up, but we'll represent that third vector to be another vector, and then do the Gram-Schmidt orthogonalization process to find a third vector here. That sounds a little confusing. The other way to do this, this, by the way, would be easier if we had a smaller matrix to deal with. All right. So, but the other way to do this is to find the eigenvectors of this matrix that we found, the A times A transpose matrix. All right. So we got 9, 4, and 0. So let's go in that order. Let's find the eigenvalues for that. Let me rewrite this matrix over here. 5, 2, 4, 2, 4, 0. And it's a symmetric matrix, so this is a 4. Oops. Four, 0, 4. Is that correct? Yep, that looks good. Let's put it aside over here. All right, so let's find the E vectors for that. E vex. So what we need to do is we need to do the 5 minus 9 lambda thing. And so we will row reduce, essentially. We'll row reduce this matrix. So 5 minus 9 is -4. And then 2, 4. 2, 4 minus 9 is -5. 0, 4, 0. 4 minus 9 is -5. So let's row reduce this, RREF. Let's see, I don't know if there's a quick way to do this. Maybe I'll just use technology to RREF that. So let's pause. Okay, after some consultation, RREF, consultation with Mr. Wolfram, I got 1, 0, and I got a -5/4. I got a 0, 1, -1/2, a 0, 0, 0. As expected, we should get a free variable. So my free variable is going to be 1 in the last component. This is going to be a positive 1/2, and this is going to be a positive 5/4. Let me scale that so that I can easily divide it by its magnitude. So to scale it, I have a 4 and a 2, so I'm going to multiply everything by 4. And when I do that, I will get 5. 4 times 1/2 is going to be 2, and then this is 4. So I can find the magnitude of this quite easily. 25, well, I don't know how easily, but let's add 25 plus 16 plus 4. That's 45, so root 45. I can probably simplify that a little bit, but I'll just leave it as square root of 45. All right, now let's put 4 in there. Subtract 4, so in the diagonals, 5 minus 4 is 1. This is 2 and a 4. This is going to be a 2, 0, 0, because 4 minus 4 is 0. And this is going to be a 4, 0, 0. All right. So let's see. Let's put this up on top and make it into a 1. So we got 1, 0, 0. And let's this will disappear. The last row will disappear because I just multiply that by 4. And then this middle row, or this first row, 1 minus 1 is 0. And then everything else stays the same, 2 and 4. So let's call it 1 and 2. And I believe that is simplified. So we got a free variable in the last component. This is going to be a -2. And this is going to be a 0 because it was zeros to begin with. Okay. What is the magnitude of this? The magnitude of this is root 5. So I got my second column. Now my third column will have an eigenvalue of 0. So this is just going to be this matrix 5, 2, 4, 2, 4, 0, 4, 0, 4. And the quick REF of this will give me a 101, 0, 1, negative a half, zeros here. And so I will get a free variable, a positive 1/2 and a negative 1. So multiply everything by 2. This will get me a negative 2, 1, 2 with a square root of 2 times, that's 4, 8, and 9. So that's just 3. All right. So if we construct a U matrix, this will have the columns of 5 over root 45, 2 over root 45, and a 4 over root 45. Ooh, come on, computer. All right, that's our first column. The second column would be 0, negative 2 over square root of 5. And a 1 over square root of 5. And then our last column is going to be negative 2/3, 1/3, and 2/3. All right, and that is that. So if we take U, multiply it with sigma, and multiply it with V transpose, we should get our original matrix A back. Okay, that's our example, and you're going to try to do the same thing. All right, good luck.